Okay, yeah, please go ahead. Sorry for that.
All right, so thank you very much for the invitation, and thank you for organizing this great series of meetings. I've enjoyed all these so far. So I'm going to talk about homological residue fields in tensor triangulated geometry, and then their connection with certain kinds of cooperations. And so really what this is, you know, we have for a tensor triangulated category, you'd like to have some notion of residue fields, and but we don't know how to do this all the time. So we can do this sort of approximation to a residue field called the homological residue field, and we can do this all the time. And then in the situations where we do have some tensor triangulated residue field, we'd like to compare that residue field that exists in examples, and then this homological residue field that exists all the time. So this is this is talking about the work of two papers. So one with Paul Balmer, and then another one with Greg Stevenson. So first, let me talk just a little bit about fields in tensor triangulated geometry. So of course, you know, in commutative algebra, we have residue fields. And if I'm working in the derived category of a ring, I can understand let's say the thick subcategories of the compact part by studying a support theory built out of just the regular old residue fields. So then in topology, there's also field-like objects, and these are given by the Morava K-theories. So the Morava K-theories are a type of they're a homology theory that has field-like properties, and we can also control the thick subcategories of a finite spectra using a support theory built out of Morava K-theories. And then in the last example I want to mention is modular representation theory. And here we have what are called the pi points. And the pi points are built out of, well, I'll just say this, if G is a finite group, pi points of the stable modular category of the group are built out of algebra maps from the group algebra of a cyclic group of order P to the group algebra of G. So here K is a field of characteristic P. So here, the stable modular category for this cyclic group of order P, it's like it's like a field. It's like a tensor triangulated field in representation theory. And so these three examples are kind of my three favorite examples, and we kind of lose various good properties as we go down the list. So for example, these Morava K-theories, the spectrum representing this homology theory or this cohomology theory, it's not always a nice ring spectrum. So at P equals 2, it's not a ring spectrum at all, which is a little bit odd. And for these pi points, we have algebra maps from KCP to the group algebra of G, but this the tensor triangulated structure on the stable modular category is built out of it's coming from the hop algebra structure on the group algebra, and so these maps aren't hop algebra maps, so we don't get a tensor functor from these maps, but still it's good enough to do the job here. So we have these are three examples of residue fields, and then we'd like to do this, you know, given any tensor triangulated category. So the big question, or the hope, would be if T is a tensor triangulated category, TT-cat for short, what are its residue fields? And let me quickly say that I've written on this question is that I don't know the answer. I think it would be a very exciting thing if someone could show that these residue fields should exist all the time. And it's not even clear just immediately what the question would be, because you would want to have a field and then a functor from your category to the residue field. And then as we've seen, it's not exactly clear what properties this functor should have. Maybe it's not even, maybe it's even too much to ask it to be a tensor functor. Okay, so I should mention that I'm going to talk about this work of Balmer, Krause, and Stevenson, and they give a good definition of what a tensor triangulated field should be in general, that at least encapsulates these three examples. So it's more like if I have a category, how do I cook up the residue field, not what should a field be. Okay, so so we don't know how to make these fields all the time, but we can make sort of an abelian shadow of these fields called these homological residue fields. So now I'll talk about those. So these were introduced by Balmer, Krause, and Stevenson in 2019. And their definition is slightly technical. So I think before I write down the definition, I'll give a theorem involving a theorem whose has a it involves homological residue fields, but that says that you can use them to see something that just is purely on the tensor triangulated category side to see that they're a useful idea. So here's a theorem from Paul Balmer in 20, and it's a very cool theorem. But the main reason I want to say it now is because hopefully you'll see that whatever these homological residue fields are, they have some they tell us a lot about the category. So here's the theorem. So if we have a map in a essentially small rigid tensor triangulated category, let's call it T, or maybe TC, T for complex. Then F, this map, it's tensor nilpotent if and only if and only if this map is 0, if and only if, excuse me. This map goes to 0 for every homological residue field. Okay, so whatever these homological residue fields are, they're enough to detect tensor nilpotence of maps. So this should remind you of the nilpotence theorem in stable homotopy theory. So it's kind of like an abstract version of the nilpotence theorem that works for any tensor triangulated category. But then you're looking at these homological residue fields rather than the Morava K-theories would be the example in the usual nilpotence theorem. Okay, so now that hopefully whatever these homological residue fields are, there's something interesting. Now let me give you the definition. So here we'll let T, so here's the definition or the construction. So T is a big tensor triangulated category, which means it's a compactly rigidly generated, compactly So it's generated by its compacts, and all the compacts are dualizable. And let's call the compacts TC. Okay, so so this category T, we can embed in this category of modules for TC, and this is just out of the functors. So this is out of the functors from the opposite category of TC to abelian groups. Okay, so TC, of course, it's inside of T, and let's call this A. That's our usual name for this. And TC embeds in here as the finitely presented part of A. So A is a nice Grothendieck abelian category. So it's a nice place to do homological algebra, even though it's sort of large looking. So a homological prime. Let's see here. So a homological prime of T is a maximal Serre tensor ideal. I guess I didn't say this, but these are tensor categories, and these Yoneda functors are tensor functors. Is a maximal Serre tensor ideal of this finitely presented part of A, and a homological residue field of T is this composition. Let me give a name. Let me give a name for this. Is T this A modeled out by the localizing tensor ideal generated by any homological prime B. So this is B homological prime. And our notation for this will be this A sub B with just look at this A sub B. Okay. So one thing that Balmer, Krause, and Stevenson proved, kind of connecting this back to the triangular category you started with, is that this tensor localizing ideal B, this is equal to the kernel of tensoring with the representable of some objects in T. So this EB, this EB is in T, and this is my notation for the image of it under the Yoneda embedding. So all of these homological primes and then these residue fields, I can understand in terms of some objects in here. But the questions, of course, would be, given a prime B, how do I cook up that EB, that sort of thing. Okay, so here's this construction you can do, and then this theorem of Balmer, says that these homological primes, have a lot of information about our tensor trinity category. But then the question when you see this at first would be, how do you end up computing what these things are in examples? Just because this category is kind of a big looking category, and you're doing this general thing. That's kind of how do you get your hands on it. Okay, so here is a question or a construction you could do. So if I have if T is my tensor trinity category I care about, and if I have a residue field let's call it K, let's call this residue field functor F. So if this is a residue field functor, so if this F hat is functor and F is exact and monoidal, and K is a tensor triangulated field, what could I do? Well, under these assumptions, this F has this adjoint. Let's call it U, and T maps to the modules for TC, and K maps to the modules for the compact part of K. There's some more adjoints there, and let's call this map. Let's call that F hat. So F hat is the induced map from modules on TC to modules on KC. And I could mod out by the kernel of F here. And this is a, let's call this A sub F. There's an induced map there with adjunctions. And it's proved, this is essentially in the work of Balmer, Krause, and Stevenson, that this category here is a homological residue field. So this is a way of getting a homological residue field out of a tensor triangulated field. So this gives us a way to access some of these homological residue fields, and in the examples we care about, such as for the stable homotopy category, or for the derived category of a ring, or for well, in some special cases in modular representation theory. And in fact, in those, at least in the for the stable homotopy category and for the derived category of a ring, I get all of the homological residue fields this way. So they each come from a tensor triangulated residue field. Okay, so here maybe the first question you might ask would be, what's the relationship between this this homological residue field and then this tensor triangulated residue field. So how does this relate to your residue field functor here? And we'll need it in a second, so I'll just oh, got a cat coming through here. I'll label those with hats on them too. Okay, so I'll answer this question here, but now is probably a good time to ask if there's any questions so far about the definition of these homological residue fields or this construction of one. Okay, good. So so the first theorem I want to mention sort of answers this fairly nicely. So it's a theorem of Balmer and myself, and so I'll say two things here. So this theorem tells us that this object of T who so this is this object who gives us this kernel of F so this is an object of T, and when I apply this map here and then take the kernel of tensoring with that, this is that kernel at F hat. So this is a summand of this right adjoint U applied to the tensor unit of K. Okay, so this tells us that we have some control over which what object this is. And then moreover, we have that this A sub f, this homological residue field, this is comodules for the comonad of this fu. So we have this this comonad here, or this comonad here on modules for KC, and we cook up this residue field, or it's comodules for that comonad there. Okay, so this is satisfying, and maybe just the main here's a quick sketch of the proof. The main part is that this f bar, this functor here, is faithful. And faithful and exact. So we have this faithful exact functor between abelian categories, and so that lets us use a version of Barbeck to get that these comodules. And then that also lets us, we have a map. Well, maybe I won't go into the details for this. It's you have to study these residue fields a little bit, but you get a splitting of this down here in the residue field. You get a splitting that the image of whatever this object is up here, down here, it splits off of this U bar of the unit there, and then you can take that splitting here, and it ends up giving you a splitting here also. Okay, so I guess this is not a proof sketch; it's more like the proof ingredient. The main ingredient is this is being faithful. Okay, so let me mention some examples here. So in many cases of interest, this U of 1 is indecomposable. It doesn't have any summands. So then that tells you what this would be. So in the stable homotopy category, so for let's just get 2 examples here. So for T, the stable homotopy category. For TSH, so SH is the stable homotopy category, and the homological prime B corresponding to a Morava K-theory. Then this object of T giving you this homological residue field is just the spectrum. The Morava K-theory spectrum, and that's just because this is indecomposable as a spectrum. Okay, and then similarly for the derived category of a ring, and I have a prime B corresponding to a residue field. So kappa P being the residue field at P. This object EB is just kappa P. Itself thought as a complex concentrated in degree 0. So in these 2 examples, you can really have a lot of control over what's giving you these homological primes. Okay. So this is a nice answer here, but understanding what this object is maybe less work than kind of understanding what this category is, this A sub f, and then understanding what this functor is. So we'd like to understand that as well. So here's the next theorem I want to mention. That's of myself and Greg Stevenson. So here's this theorem of me and Greg. And what does this say? This says that if I have a residue field functor, where mod KC is graded R modules for some ring R, and then if C is the associated comonad, so this F bar U bar comonad on the modular category for KC, then we have that if I apply C, so this comonad to my tensor unit, which is just the ring R, this is a bialgebra and this category A sub F, this category of homological residue fields, this is comodules for this bialgebra CR. So I can identify this comonad as some or is just given by tensoring with this bialgebra. So then I have a more concrete description of this thing depending on your point of view. So the point is that in many examples, just going back to this picture here, this K, it's a tensor trinity category, but it's in some of the examples, such as in topology, it's also an abelian category. So it's like a semi-simple tensor trinity category. It's like it's that kind of silly case where it's also an abelian category. So for example, if I'm looking at the residue field corresponding to the Morava K-theories in the stable homotopy category, this K, it's the homotopy category of modules for these Morava K-theories. But then it's just the category of graded modules for the homotopy of the Morava K-theories, which are a graded field. And then even more simply for the derived category of a ring, this K, it's the derived category of the residue field, so it's just graded modules over the residue field. And in that case, this map to the module category for that is just an equivalence. So then you have this comonad on a nice abelian category in those cases. So then we have this theorem that's identifying the comodules the comodules for the comonad in terms of comodules for this co-ring. Okay. Very, very good here. So let me give a few more examples here, just kind of talking about places this applies. So the first example would be in the stable homotopy category. So the homological residue field corresponding to these Morava K-theories are comodules for just the cooperations for Morava K-theories, Kn star of Kn. So here, if you if you apply this theorem to the case where you have the stable homotopy category mapping down to Kn star modules just by taking Kn homology, this is its own. This is also the functor category for the compact part there. So then you have this map to the modules for this SH. And you have those there. And then this is mapping down to the homological residue field. Let's call it A sub, maybe I'm changing my notation here. Let's call it A sub Kn, the homological field corresponding to Kn. So when I apply this comonad here, it's just the same thing as going around, and the same as going around that way. And so that's just this functor here. This is just the functor for getting down to SH. So when I apply this functor to the unit here, it's just taking the Kn homology of Kn. Okay, so that's a nice description of this homological residue field in terms of something that's studied elsewhere in topology. Okay, and then the exact same story, just the same picture here works for the derived category of arene, and I'll mention that separately. So for this map, let's say I have this tensoring down to the residue field here. The homological residue field is comodules for the Tor coalgebra. And again, it's because this derived category here, it's already an abelian category. And so when you it's its own model category. And so when you do this this comonad, when you apply it to K, you just have, or to kappa P, you just have you just first get down to R, and then you tensor back to kappa P. So you just have kappa P tensored over R with kappa P. So that's just the Tor here. Okay, so these are the two examples, kind of two favorite examples of tensor Triangulated categories, where we have a very complete understanding of these homological residue fields, and then how they relate to the tensor Triangulated residue fields. So I mentioned modular representation theory at the beginning of the talk, and maybe I'll spend the last few minutes. I'll probably end up stopping a little bit early, but I'll spend the last few minutes talking about the case, what happens in modular representation theory. But before that, are there any questions so far about these theorems or these examples?
I was just looking. I think that Tor coalgebra goes back to John Tate in some archaic time, like 1955 or something, in a paper in the Illinois Journal of Math. It's a great, beautiful object. And somehow it took a long time for it to get noticed, I think. Other people may know more about it than I do.
Yeah, I've come across that paper. I didn't exactly know the history. I mean, I get the I get the impression that this isn't maybe it's thought of as a formidable object, but it
John
it should be.
Moore,
It has lots of information.
Yeah, Haynes Miller says John Moore loved to drink bourbon and talk about that thing. but he didn't apparently.
Yeah, well, here's another place it comes up. And I should mention, just for these two examples, there's the story that works. There's a very similar story for even periodic ring spectra. You can do a construction of residue fields that works just kind of like the derived category for a ring. It's sort of one step away from just the discrete case. And so there you have a good theory of residue fields, and then you have the same theorem here, where you can cook up these homological residue fields, and there'll be some sort of Tor coalgebras for the residue fields that exist. So then I should mention, because I guess group theory was the title of this series of talks. What happens in modular representation theory. And maybe just to go back to this picture here before I mention it, we have this great diagram here, and so this diagram kind of constructing these homological residue fields, and we had this assumption that F was a monoidal functor, and the point of it being monoidal is just to guarantee that this kernel of F ends up being a tensor ideal, and that's sort of all you need to get going. So I mentioned these subtleties that happens in topology, where these Morava K-theories aren't always fields. So you can't always make this functor in the SH case. This functor is not symmetric monoidal. It's just monoidal. There's some issue with the grading there. So being monoidal is enough to get you a tensor ideal over here, and that's all you need to get going. But in representation theory, if I have if this is a pi point here, let me come down here and just draw the same diagram. So if I have the stable modular category for say for G, and then mapping down restricting along a pi point to the stable model category for KCP. So this functor is not a tensor functor. It's not monoidal. So our theory kind of doesn't get off the ground at all, which is a little frustrating. And then you could ask, and I think it's a question I've wondered about a little bit, is that there's this funny thing where this functor isn't monoidal, but the kernel of this functor is still a tensor ideal here. So you do get an induced functor on model categories, and then you could ask, is the kernel of the induced functor on the model categories, is it still a tensor ideal? And then if it was, the theory would get off the ground. But what could you do instead? You could change your tensor structure, but to make it be a monoidal functor. So let's look at E. Let's let E be just a abelian P group. This Z mod P to the N, and so then this group algebra. So we're in characteristic P. So this group algebra just looks like x1 xn mod these xi to the p's. So we could put and then this KCP, it's just this KT mod T to the P. And we could put an exotic hop algebra structure on these group algebras. So let's put this hop algebra structure where a co-multiplication takes T to 1 tensor T plus T tensor 1. And then similar with the xi's up here. Okay, so this is part of this hop algebra structure. That's not the group hop algebra structure, but these are also you can think about these as the restricted enveloping algebras of a P restricted Lie algebra. And in that case, this is the Hoff-algebra structure coming from there. But if you put these Hoff-algebra structures on there, then this map, this pi point, which is just taking just takes T to some linear combination of the xi's, that is a Hoff-algebra map then. So then you do get a tensor functor. So then we have with these exotic tensor structures, you do have this here. So then this is a tensor functor with this exotic or this different tensor product. So then our theory does go through, at least the theory for Paul and me. So you have this, you have that the pure injective or the objects of this category who's giving you the homological prime is a summand of this pi lower star is just obtained by homming back to KE. So you do get a summand of that, but it's not obvious that it's indecomposable anymore. So you don't have quite as much control. But then in Greg in my paper, we worked out that in fact, this modular category, for the compact part of this, is modules for a ring. And this ring R, this is the endomorphism ring of the sum of the indecomposables. And in the stable modular category. So you do have this ring here, but now it's not modules over a field or a graded field, it's a more complicated ring. But then this does, at least in this case, give you a description of this homological residue field in terms of some comodules for some slightly more mysterious bialgebra. Okay, so I'll stop there. Thanks a lot for your attention.
Thank you, James. Yeah, let us all unmute ourselves and give the speaker a round of applause. Okay, if you have any questions for James, please unmute yourself and ask the question, or if you want, you can put them in the chat. Actually, I'm not sure if James can see the chat, but yeah.
I think I can actually.
Okay.
But I think I see Dan's hand that's up.
Yeah, so I'm looking at your last example. And so suppose you start with the restricted P-Lie algebra. And so you can actually represent the pi points in that situation by primitive elements, just like you did. So can you just, can you just apply your theory to these P-Lie algebras, the restricted enveloping algebra, the P-Lie algebra, and what can you say?
Yeah, I believe you can. So I'm not so familiar with the story for the P-restricted Lie algebras, but I believe in that case you do get that the pi points are Hoff-algebra maps, and then so that you get a tensor functor, and then yeah, you can apply our theory completely. And I think yeah, no, I think it's still I think everything still works. It's just this this ring R is something a little complicated. So trying to figure out explicitly what these comodules are, it'll be some at least unfamiliar to me looking by algebra, comodules for some.
So in
But
general,
then
so
yeah,
in general, the restricted Lie algebra situation is the nicest case of pi points for modular representation theory. So yeah, I think it'd be really nice. It'd be really great if you can just kind of work that out, and then, you know,
yeah, no, I agree. I think in figuring out what this bialgebra is, and some other examples would be a worthwhile thing to do.
Great. Thanks.
Thank you.
Thank you, Dan. Do we have any more questions for James? Yeah, please go ahead, Jack.
May I just a remark about the case P equal 2 for the KNs? They actually are behave better than you might think. This is sort of one of the last things that Mike Boardman did. It turns out that that there are sort of two multiplications at the prime 2 or two compositions, and they're interchanged by a Bachstein, or they're related by a Bachstein. And if you think of the product as over the ring generated by the mod 2 Bachstein, it becomes symmetrical monoidal. I actually learned this from Nick Kuhn, but I don't know that it's written up anyplace. It's in late work of Boardman and Wilson. They talk about the spectra PN, but it really descends to the KNs.
Okay, interesting. Yeah, I think I've heard. I think Nick might have told me a similar thing one time, but I don't know if I fully understand that. So that would be it'd be really nice if you could somehow, you know, maybe I think is what you're saying is there's some other functor to some, you know, slightly fancier category that is symmetric monoidal, and so that would be you know, you could hope for a similar thing to happen in the representation theory case. Like maybe there's some other category, you know, built out of these pi points that's, you know, just a slightly different category where then you do get a symmetric monoidal functor, because it would be, you know, you would hope that you could always, that your residue field functor, you know, you would hope that it would always exist and always be symmetric monoidal. So maybe that's nice evidence for that.
Yeah.
For that hope.
Yeah. Very nice talk.
Thanks.
Thank you, Jack. And yeah, it was a great talk, James. Do we have any more questions for the speaker? Let me go through the list of participants to see if anyone has got their hand up. No? Okay, if there aren't any more questions, let's thank James again. Right, so the hand symbol that comes up when people clap is different from the hand symbol that comes up when people raise their hands to ask questions. Anyway, yeah, thanks again to all of you who attended this talk, and a special thanks to those of you who came from very difficult time zones. Next week we have Beren Sanders speaking, and the week after that we have Fernando Muro, and then I think Luca Paul and Paulo Stellari. Yeah, I hope to see you guys soon at the next week, at the next talk. Okay, thanks again, all of you for coming.
Thanks for organizing.
Yeah, no problem.